cloud compute, I'll just give you an example of what we had to do at AMD to be able to handle the complexity that we're facing. And that is we went actually to a hybrid on-prem and cloud compute infrastructure for our EDA. And we're leveraging constraints. First it was, conflicting constraints, one versus another, then triple constraints, quadruple constraints. Because you think about it, every new product, you have these performance goals.
Oh, hi.
And the world's best full performance processor, FX72F3. With the introduction of Palladium Z2, we're seeing an impactful improvement in workload throughput. And the same design running on Palladium Z5, as if the very foundation of the design itself.
Very good.
Should I leave it on video? Yeah. Okay.
We got Matthew in the house. We got Warren in the house. What's up, guys? How you guys doing? What's up, man? Good to see you. This is our crew.
NetApp, Microsoft Azure, and Google Cloud. Our first speaker for today, Flo, brought up PlaceItNow for advanced process nodes and led physical design for multiple graphics takeouts. Mr. Sankey holds a degree in electrical engineering from Queen's University.
Go.
that getting into the chip industry would help me with that. It has not. But I still like to play computer games.
Good morning. My name is Quang Nguyen. I'm the CAD manager at AMD. So my current responsibility at AMD is really to define methodology to do post-layout simulation and verification, i.e. electrical analysis. So that includes extraction, clock mask simulation, EM/IR analysis, and so on. Prior to AMD, actually, most of my career was in EDA. So in my early career, I worked on logic simulation. I worked for a company called CAD Artisan. Many of you probably never heard of it. It was a first Verilog compatible simulator that was in the 1980 something. And then in the mid 1990 some, I heard deep submicron, and that became like a so hot a buzzword that I quit my front end job and focused on back end and joined a company called Simplex Solutions and working on extraction and IR drop analysis. So that was something. And then after Simplex Solutions got acquired by Cadence, I was the product engineering director, supporting extraction and EM/IR. The EM/IR today, you know, Lotus. So after that, I joined a company called Silicon Frontline, doing a 3D power device simulation. And after I got sick of EDA, I joined AMD. So that is my EDA career. So get back to the first question, what brought me into electronics? So in 1972, when I was a young boy, I got given like a Radio Shack electronic kit with like a few transistors and a solar cell and a few diodes and capacitors and resistors. And I was able to design like amplifier and all kind of crazy stuff. And this young boy got fascinated by electronic design. And then in 1980, so this young boy decided to risk his life on a draft for 7 days, 7 nights, to come to the US and to become an engineer. And I worked through the industry, so from like a few transistors, now I got an opportunity to work on design with billions and billions of transistors, so that was something. And I'm kind of happy to be in this business for a long time, and I feel very, very satisfying with all the things that I accomplished and I'm seeing like at work with the industry. It grows so fast and so efficient and so fascinating. So that is my whole story about how I got involved with electronic designs.
Thank you. Introduction to the topic today is 3DIC. I was hoping you could tell us about AMD's efforts into 3DIC, chiplets, etc. I think AMD would be considered on one of the forefronts. So can you briefly introduce what you're doing at AMD and how you got there?
Yeah, I cannot really go into very specific about what AMD is doing, but definitely 3DIC is one of the major focus at AMD to make our product more competitive and to get capacity, performance, high power computing, all that stuff together, right? So we've been working on 3DIC for a long while, and I'm more focused on sign-off methodologies, right? So our focus is really look at 3DIC design and how to figure it out, how to sign it off and make sure that it's working properly before we go to silicon. So that is really a true trying effort, and it requires a lot of collaboration between AMD and in this case specifically ANSYS. Because if you look at from the industry point of view, there is no such methodology in place how to validate, how to qualify a 3DIC design to get it to the point that it's good enough to go to silicon. So that is really a multiple years effort between AMD and ANSYS to get there. And then recently we also need to enlist the help from Synopsys with 3DIC compiler, because I think like the amount of data that we have to deal with IC design is humongous, right? You're not just talking about one or two chips, you're talking about 10, 20 chips together with an interposer. So the amount of data is really massive, and it's come from all areas, from all the, either from different tool, different package, and how you put it all together. So that's the data management is one thing. And another thing, like, if you look at the way you do analysis, like even it's very challenging to do a sign off with a single die. Now we do it with 3DIC. So it's the challenge there is the amount of data. And I don't think there is no compute resource available today that can do 3DIC, the whole design together, right? So the key thing there that we have to decide is divide and conquer. And what part of the design is critical and how you divide and conquer, that's also critical. And then we go into different iterations before we came down to must, should, could, right? What are the key things that we have to do in order to have a good confidence that we can keep up, right? So that's the must thing. And even that is really go to number of iterations before we come to that agreement. And then one of the biggest challenges, this is not a new problem, but it's an old problem, but it's become a new challenge, right? I think the interposer in general, it has a lot of complicated shapes and also big, right? And the team today is like using 2D tool for 3D IC, right? For the 3D world. And the challenge there is using 2D tool to do to recognize like odd shapes and all that stuff. It's really challenging, right? And one of the challenges we have is how we know that a violation is a real violation or false violation. So there's a lot of work there in that space. I think like ANSYS makes good progress in that area, but that is one of the challenges. And then once we're done with that thing, I think the next thing is really we start look into that. Turbo become really, really important, right? So for a single die, we're approaching like half a kilowatt. So if you throw a few die together, you're talking about kilowatts kind of design. So how you manage the thermal, how you know where the hottest spot, all the issue with thermal is really bubbling up. And again, using 2D tool today to solve the 3D IC problem, it's really a stretch. That is also really challenging. And another thing like to me is also the HO problem, is inductance. You know, in the interposer, you have long lines, so you have transmission line effects. So you need to extract inductance. And that's another challenge where we have to take the 2D tool today to do analysis on the 3D design. And you facing there again, capacity, performance, accuracy, all that stuff becomes very, very challenging. So AMD, we have to be creative, right? Because for the lack of EDA tool readiness, we need to be creative to find a way to get to the point that we say it is good enough. So that's really the challenge for AMD is really what is good enough for us to tape out, even though we run into all kind of limitation of the 2D world. So that's what's going on.
John, do you have comments, follow?
Yeah, I'd like to comment. Co-op, first, you raised many good points. I'd like to use the interposer as an example. I mentioned in the beginning that the lines between silicon and system have blurred. And we can look at the tools that have been used at the package and board level, where the effects that Henry talked about, rigorous 3D electromagnetic analysis, transmission line effects, inductive cross-coupling, these are now the problem of a chip designer, because these interposers are driving such high signal speeds, right? If you have AI chips and HBM, that interposer indeed is very much like what we used to do on package and board. So bringing those techniques and solvers like HFSS and Raptor into the IC design flow is a challenge that many of our customers, we're working with them to partner with them as well as the foundries. There's also a second thing that I mentioned here, I wrote down, is that there's a people or organizational challenge here. Many of the companies, right, traditionally you have a chip team and you have a package team. But now we have 3D IC, and so who's responsible for the interposer? A form of that people challenge is, now we're talking about thermal, is there a thermal architect? What's the thermal methodology? So you might have thermal awareness in the chip team and the IP team and the package team, but who really owns this problem? And so these are people challenges, organizational challenges, in addition to the technology challenges we talked about.
Yeah, I agree with John that I think like 3DIC not just tool itself, but also methodology. And also people like, example like John mentioned thermal, right? We have to work with other people really not in electronics, it's more on mechanical. So how, we speak with different language. So how we do the proper communication, make sure that everyone understand the same language we're talking about, it's still a challenge. Yeah, so I think like moving to 3DIC, not just the tool itself, the methodology, the mindset, the knowledge, all that need to be transitioned into a true 3D IC design environment, right? So I think the transition is really just happening. It's now, it's just starting. It may take some time, but I think it's moving fast. But I have reason to hope that a lot of these things can be solved in a short period of time.
Henry, do you have a follow-up?
Sure. I think we really agree with a lot of what's been said. We've been partnering with ANSYS very closely, also working with partners like AMD and such. There's a lot of things that really resonate. I started work in 2D world for 20-something years, leading a lot of our advanced node foundry enablement, and you see it kind of hitting the wall, and then the need really to go to the next level. So 3D had always, we all know it's not new, so we've been keeping tabs on it, but it's probably in the last few years, about maybe 4 years ago, we really recognized this is becoming commercially significant, right? And you want to, when did Noah build the ark? It was before the flood. Right? And so then we started embarking on this endeavor to look at all these challenges, the amount of data that Koa is talking about. For today's most advanced 3D ICs, there's more transistors on that 3D IC than there are stars in the Milky Way galaxy. Really, I mean, think about it. There's over 300 billion, transistors on a 3D IC. That has to work, and that's just an incredible engineering feat that kind of stuff works. And the amount of data and the diversity of data, all from different types of tools, of different backgrounds. For the first time, we're hiring mechanical engineers as part of this because. I think a lot of these kind of systems analysis, for 3D ICs, thermals, EMIR, these now become kind of first-class objectives. But they need to be taken not just at the sign-off stage. Now we're trying to work with ANSYS to bring this forward at the design stage, because as soon as you split up that 2D die into 3D, you've just entered into your system design, and if you make a mistake there, there's no way you're ECOing your way out of it. Once you get into your 2D die execution. So you've got to make sure there's some sense of rigor at the beginning stages where you're not just using Visio and, I think that's what people do, right? And then, do some hand calculations. Can we construct a framework to bring together all the thermal, EMIR, design, package, systems, architecture, all these different folks? Some people are on Windows, some people are on Unix. Can we bring them all into one system now? Because you're all working, this forces everybody to work on the same system at the same time. It's no longer this kind of a handoff model. So that's really what we envision as a platform. And I would say you can't do it all alone. People look at different foundries, they're getting technologies from all over the place, because this is really a huge, huge space. And so, that's why we value our partnership.
So, everyone agrees with the thermal issues, but liquid cooling is a potentially fundamental solution, but it doesn't look like it's on the near future. So, what's the thinking around in the panel about liquid cooling?
Comments? You've stumped our panel.
Well, you may not realize, right? But the latest supercomputer from AMD, they all really, we use liquid cooling to cool it down. So it's there already.
Yeah, I think from my perspective in space, there's one thing I don't get that you get here on Earth, and that's air. I don't get any convection cooling, right? So just to make it a little bit more difficult. But so I think the key thing is you know, over at Xilinx, they hired a chief thermal engineer. It's one of probably the best hires that I think Victor made over there, recognizing that the thermal effects need to be included in the analysis before you're building the product, not as an afterthought, right? So we have to solve these problems. And that chief thermal engineer had a meeting with the Lockheed Martin thermal engineers just last week, because again, as we look at how we do the thermal dissipation, you know, we're a lot more like a cell phone than we are, you know, a data center type of an application. And how you conduct the heat away from the device is key. So all of these new technologies for keeping the system and the device cool and within reliability operating temperature ranges that give us the longevity for these missions that we need, it's so critical that you really can't go forward until you know you have a solution for it.
Yeah, so part of thermal is not just like how to keep it cool, right? But you need to be able to monitor the system to make sure that the heat don't get to the point that it really burn down the wires or burn down the device, right? So one of the things that we're looking for is to determine where to put the sensor to monitor the heat in the system, right? So it doesn't get to the point that it's got too hot and everything shut down. We need to have some kind of smart built in, so it gets too hot, we need to throw it back down. So it's still in the operation mode, but not going down. So thermal to me is not just like how to make sure that the system doesn't get too hot, but it's also making sure the system functions properly, even the temperature getting too hot. Right? So that's another aspect of thermal.
Yeah, our chief engineers at Lockheed Martin, they always want to make sure that they have some data available to tell them how the system's operating, right? Because it's typically remote and it's autonomous. And so when we're talking with all of our programs, where you're doing your thermal monitoring and where you're using those PN junction diodes to monitor the temperature, all that data is absolutely needed, and you need to be thinking about that so you can take appropriate action when you see temperatures are getting to a dangerous point. Right?
Yeah, I would also comment that, maybe follow up what you're saying, you know, within a certain thermal profile, it's all about what performance can you get out of that, reliable performance. And so if you think, right, in popular press, you look at the processors from Apple, right, the M1, M2, you know, famously, you take a MacBook and it can run at high performance without firing up the fans, you know, having, you know, longevity on battery. And that dynamic thermal management ties into the sensor placement, as well as being able to simulate in advance what the real workload will induce thermally onto that system, so you can get the best-in-class performance. So that's, you know, even with the best cooling, you're still, I think, in many applications, trying to push performance as hard as you can. You know, the model processors also benchmark against each other, and so depending on how fast you're able to run under real workloads, that dictates, you know, how many slots you get into the latest model.
Yeah, I would add on to that. It's all kind of related. You know, you can do liquid cooling, but you know, regardless of how you cool it, there's always how can you optimize the thermal, natively within your system, and it's all interrelated in the sense that your performance, your EMIR, multi-physics, all these things. There's a cascading effect that happens, and so how do you tie it all together in a way that designers can really manage this?
We're talking a lot about using a lot of advanced technologies in the packaging world and all the stacking and the bonding and everything going on from suppliers. Do we think that they're ready in terms of the technology providers, in terms of the reliability work they've done on the TSVs and all the technology and how it's going to survive over all the stresses that's going to happen in the environments? Are they ready for us, or are we pushing them too fast?
John, are we ready?
Yeah, I think there's been a tremendous amount of work that's been put into advanced packaging, starting with the foundries, but also with the OSATs. And whereas many of the design challenges we've talked about today are, we're pushing the envelope. In reality, there are many different areas where 2.5D techniques have been in place, and some for 3D for a while. Memory is one, FPGA is another, high-speed networking. So, to the point made earlier, or maybe a different form of the point, engineers can design with slide rules, right? As long as we know how to design things. So I think there are, from my perspective, enough proof points out there.
I don't know if everybody was at the TSMC symposium, but they mentioned that 10% of their capex is for packaging, which is quite high for a foundry. So there's a huge amount of focus on it. Any other questions?
Hi, Daniel. Right now, the James Space Webb Telescope is in the news, and it has a thermal shield there. It's like, on one side, it's so cold that the video camera that monitors the instrument cannot work. And the other side, on the sun, it's so hot that it's like they cannot do anything in terms of image or whatever. Correct? It's like, and recently also they had like micrometeors that nicked the telescope. Right? Can you comment the challenges on the extremely hot, extremely cold, and the micrometeors? Thank you.
I guess that one's for me. So you're talking about the James Webb Telescope, and I think, as a person who's interested in space, I'm very excited for that program. And it's interesting that I've been working with the various different team members on the JWEST program for almost 20 years. Right? That's been a long project. There's a lot of expertise that went into modeling and understanding the radiation environment and the micrometeor environment and expectations. As I talk to my colleagues at NASA about James West, I'm not directly involved with it, but as I talk to them, it's all within what they predicted from their modeling and their analysis, right? Which kind of speaks to the importance of the EDA tools around these types of products, whether it's predicting the micrometeor environment, the radiation environment, the thermal environment, all these things. We have to be able to model these things before we go spending the money we spent on JWEST. And hopefully it gives us the answers that we're seeking, but we'll see. I don't know if I fully answered your question, but sure. We can talk offline a little bit more. I think the thermal challenges, there's a whole set of folks at Lockheed Martin that focus 100% of their time on understanding these types of thermal challenges that exist and coming up with novel solutions for them, which, again, when we started having conversations with the Xilinx on their Versal product, we got the thermal engineers between the two groups talking to each other, because I'll tell you, they speak a different language and I can understand 90% of it. It's the other 10% that worries me. I think they're communicating, that's the key.
Any other comments? All right, I want to give this one more try. So we're just going to do the last three numbers. Are you ready? 371.
There you go.
You can just, you got one. 372.
Rich, over there.
373. Somebody didn't mix the whole. Okay. So do we have any other questions from the audience? You, sir.
Hi. Coming from the chip design world, GDS and OSS has been the standard for layout. Is there a move or to standardize package layout or bring some of it to the OSS world, or how can, when you're doing design and now you're model, as you're saying you're doing extract long interposer lines, you see need to do that extraction early on rather than wait for the full design to be done?
Okay, maybe I can take that. I think there's a couple of questions in there. One was on extracting long lines. Another one was, on package and models and things like that. So with respect to, I think both of them, it's important to establish, like I said earlier, some more rigor and some models there. That's going to be key to being able to scale out the solution. With respect to kind of the package side, that's one of the observations, coming from silicon also myself. It's a little bit interesting where I think common practice is, for rule definitions and things like that, here's your PowerPoint, and then it's up to the package digest that and make sure whatever they come out with meets spec, and that's to us it seems a bit ad hoc, right? And so our view, one of the first things we did when we entered into this, if you think about heterogeneous integration, you're bringing in multiple die from multiple nodes, potentially multiple sources. Where do the rules come from? When I put it together, there's die distance rules, there's kind of density rules and things like that. And so we constructed a language called multi-die exchange format, MDXF. And that's part of our efforts to try to put a little more framework around this, to formalize it a bit, where there's an ability to express these things, and so that one, there's more formal checks that engineers can actually check these things. Like Koa was saying, you're stitching together a bunch of 2D tools in the past. There's nothing that will tell you that when you put two 2D chips can be completely fine. When you put them together, the bumps don't match up, right? Or just simple things like that. People use a lot of times Excel for specifying parts of the design, and it's actually amazing. It works great until it doesn't, and there's we're hearing it's hitting the capacity limit. Excel was never designed to design chips, and then there's also floating point differences that maybe you didn't see it in the spreadsheet, but there's floating point differences that cause mismatches, and if you find that out in production, that's a terrible thing. And so you're right. As we pick at this, there's a lot of different areas where you need to really start putting in more of the central models. It goes beyond that, as we look at timing and interface models. These are things on the silicon side that I think are a little bit more evolved. It's a different kind of problem set. I think the package and so forth has its own challenges. But can we bring that level of modeling so that all these different teams, people responsible for different parts of the design, can actually collaborate a little better and more convergent?
I mean, there's a definite need for standardization of these exchanges and these methodologies. It's unfortunate Chip's not here. We've taken a shot at Visio, now we just took a shot at Excel, I think. So Microsoft isn't here to defend themselves. I don't think that most of the engineers in the room could probably survive a project without using Microsoft Excel.
I actually complimented it. It was never intended for this.
It was never intended to do this.
So I want to add to this one, like the data exchange, I think people kind of underestimated the problem. But for us, data exchange is the biggest headache, right? Example of that is interposer. Normally people use interposer using like different packages to design interposer, and normally this is not even in GDS, right? You're lucky if you get it in GDS. But then most SOC tool focus on SOC tool, they're not really dealing with GDS or OASIS. They mostly left depth, right? And then how do you translate the GDS into left depth so the 2D tool can understand? And a lot of time when you do the translation, you make the data unusable, right? So you garbage in, garbage out. So you do the translation already bastardize the format, bastardize the layout. And so when the 2D tool consumes the data, it produces all kind of garbage, right? So to me, that kind of thing is, it kind of sounds simple, but causing a lot of headache for us, right? at the early stage when we do the 3D IC verification, data exchange format to me is really one of the critical problems, right? Because the translation a lot of times, it costs a lot more easier for the downstream tool. So one, I really want to bring attention to both ANSYS and Synopsys in this space. When you do the 3DIC environment or you create this platform, pay more attention to the data exchange because that is really can save us a lot of time and headache. Even it sounds like simple, but we spend a lot of time debugging this kind of issues.
Question?
Following up on those comments just now about data and data exchange for John, is ANSYS's Minerva technology or brand suitable, as we've been talking about here this morning, or is it really more suitable for your industrial business?
Yeah, so it's a great question. Thank you, Jay. The use of more modern systems such as Minerva that do simulation process data management and also have official means of handoff is something that I think because the semiconductor industry was amongst the first to really adopt these software-driven methods. Semiconductors behind other industries in using these types of systems. And so, today when I look at my life as an employee of ANSYS, many of my systems are automated through success factors, for example. I'm no longer just sending emails, dropping a file and say, please look here. So I do see opportunities, especially as we talk about that, the challenge of multiple chip design teams, perhaps in the same company, maybe not in the same company, working through 2.5D, 3D, talking about thermal and all that. Instead of using email and files, there is a lot of opportunity for more modern systems. So to answer your question, adoption of systems like Minerva and semiconductor is an opportunity, but it has not happened yet.
In case you didn't notice, the people who are asking questions are getting one of these NFTs.
Yeah.
So, and if you ask a question that's flattering to ANSYS or Synopsys, you get 2. So, are there any more questions?
Over ANSYS and Synopsys, so great.
One more?
Henry, you are great.
Any other questions?
So, my background, I actually now work for Synopsys, so full disclosure. But worked for Intel and Altera before that. And a lot of 3D packaging was very manual. Just brute force, put it together. And it sounds like, if I listen to Dan, I listen to Ko, that we're still kind of there, right? We're not fully automated. But I'd love to understand this from Dan and Ko. What would you like to see? And then on our side, on the Synopsys ANSYS side, what do we have and what gaps are really critical to be filled right now?
AMD perspective?
Yeah, okay, so before I answer that question, I really want to put some lighter note on this thing, right? So NFT, so a couple of years ago, like when we were still in the middle of the pandemic, right? My daughter, my older daughter, she worked for a high-paying job for a company in San Francisco. And she came home and said, Dad, I quit my job and go and join a startup company doing NFT. And that was in the middle of the pandemic. And when she said, NFT? I even don't know what it is, right? So I have to go on Google and try to figure out an NFT. And she moved from San Francisco down to downtown LA in the middle of the pandemic to join a startup company doing NFT. After 2 years, I think she's doing well. So that is one thing about NFT. Like I thought I work in high-tech area, but I even don't know what NFT is. And then I have to do Google search and all that stuff. So it's very fascinating, like see how technology evolving, and even like us working in high tech, we don't even know, like which is only cover a portion of high tech. So interesting. Back to the question about what I really want to see. You remember, like I say, much should good, right? So for 3D IC right now, we pretty much like good enough, right? The must thing, right? We need to do. But if you look at the overall, the capacity performance and the automation is not there yet, right? And when you talk about 3DIC, it's not just the tool itself, but it also involves methodology and all that stuff, right? Because let's start with a single die design, right? Like we do in EMIR today, it's mostly still flat. Even at AMD, our chip is so big, we cannot even like do EMIR full chip. We have to do the partitioning, right? And I feel like there are opportunities to do more better there, and it's involved both the tools and the methodology. In the end, capacity, performance, automation is key, right? And 3DIC is not there yet. But that's where it's important to have, and I feel like yesterday at the keynote speech, he talked about the partnership between design houses with EDA. Part of that is 3DIC is getting very, very complicated, and it requires tight cooperation between design houses and ED vendors to get there. And what I'm really doing, like in the past several months, AMD works really closely with ANSYS in the past several years on 3DIC. But in the past few months, we also really want to have a tight collaboration between ANSYS, Synopsys, and AMD, because 3DIC is not one company problem, it's not one ED vendor problem. The problem is so wide, so big. We need to get collaboration from multiple vendors, multiple design houses, together to one that we can address capacity, performance, accuracy, usability, and it's involved. It's not just tool, but I think there are things that we do in design that we may need to change in order to get all that aspect up. And I really also want to address not just the must thing, which is good enough, to the should and could, right? And so that really, put it this way. I felt like I've been in this business for 4 years. When I first started out, they're like RTL, Verilog, and all that stuff is really exciting. And I felt like I involved with that. And then when we go to deep submicron and talk about EMIR, I joined a company that do EMIR, the first company doing EMIR. And when I did EMIR, nobody even know what EMIR is, right? So we got to create a market for that thing. And now, I have an opportunity to work on 3DIC. And I think 3DIC is almost like the first generation of EMIR. There's a lot of people even don't know what EMIR is, right? And we create a market for it. And now, no one can sign tape out without running EMIR. And I think 3DIC is almost like the same thing. It's the early stage of the game. And I think in a year or two, we probably see a lot more progress in this area. And I think I'm kind of excited to be part of that.
John, I have a question. Yeah. What market segment is most advanced in 3DIC, and what market segment do you see that needs the most help? So 2 questions.
Well, you stumped me there. I think the challenge came out pretty clearly today that power thermal, right, is a large unsolved challenge. And to follow up on what Koa was saying, I'd say that just like Car4Me, we came up with the ASIC design style. There's a need to do something like that at the 3DIC level. One of the most amazing announcements I saw in the past year or two was the announcement around UCIe, where for chiplets, Intel, TSMC, and Samsung, fierce competitors in the foundry marketplace, came together to align with many of the semiconductor leaders on, what are the standard definitions for chiplets, right? So that speaks to everything that has been talked about the last 10, 15 minutes about standardization. And, I like what Koa said. It's inspirational also that, we, in this room here are part of a revolution that's happening. And so, once this is all said and done, and Henry's team has tremendous opportunity, it's going to be exciting to see what we're able to do. The last thing I'll say, about flat versus other methods, just like you probably wouldn't simulate your full chip using SPICE. In the same way, some levels of abstraction are needed, and so fortunately today we have the compute as well as the mathematical methods for using AI/ML to generate reduced order models. And so and you think about then thermal awareness, how do we tie that in with, instead of doing full flat for the number of stars in our galaxy, right? There are probably better techniques, and so we have all the tools that we need to be successful here. It's just a matter of ironing it out. The easy parts, I don't know that anything's easy. which is job security for anyone that's in this industry. Thank you.
How about you, Henry? Do you have some thoughts?
Yeah, I'd add on to that. I do think we're at the early stages, and going back to what Ko was saying, it's kind of a self-fulfilling thing. Today, by definition, you're okay because you're able to do what you do today. But if you take examples of like HBM, HBM2. A lot of people did those kinds of implementations manually. You go to 2E, it gets a little more complicated. You go to 3, it gets a lot more complicated. And this kind of integration allows tremendous more bandwidth opportunity, but that also means a lot more complexity. So that's one aspect. The other aspect is where I think is really interesting. I agree. It's not just tools alone, but tool sets that are reflections of how 3D IC, the 3D IC community designers figure it all out and how to put all these very disparate workflows into their own kind of organized workflow, and what kind of framework can support that. That's your job. That's our job. That's our job. Yeah, because there's you see different needs from different companies doing different things, and by definition, they all kind of evolve their methodologies in different ways, and that's one of the challenges we see. Just the permutations of the types of things you can do is quite a lot. So how can you be flexible without trying to boil the ocean, right? and bring some kind of closure?
Final questions from the audience?
Yes, a quick question about, John mentioned that blurring the lines between 3D ICs, blurring the lines between package and chip, of course, and then Jacob mentioned all the many different technologies and permutations available from many different foundries. To what degree are the foundries getting involved in this packaging or dictating the flow or helping shape that flow? Is there a change in the way that the foundries relate to the design teams because of 3D IC?
I'll comment first. As Dan said, there's increased investment in packaging-related technologies, right? But that also, you think about foundries. Foundries provide PDKs and certified flows. So we see much more involvement from foundries looking at our package and board tools like HMSS and IcePack. And so, whereas packaging was kind of a secondary concern for the these foundries, it's now become a primary, driven by their customer asks. And we're probably very much in the midst of bringing silicon, or the lines between silicon and the system are blurred. That blurring has occurred very much at the foundry space too.
So I can speak for my hope and expectations. My hope and expectations are that they understand that their market is the custom microelectronics market, and this is the next growth phase for the custom microelectronics market. And you can either get on or you can get off. Right? They need to make decisions, and I think as manufacturing partners, we're hoping that they get on, right? Because again, we're at close to the end of transistor scaling. The next leaps in terms of computational capability is going to come from this technology, so they better get on board, right? And I think, you look at TSMC and they're clearly on board. GlobalFoundries is getting on board. I don't think they decided to get off the board. They're not shrinking anymore, but so they really need to focus on this for us to all be successful. And then, in this last conversation, we're looking for standardization of methods, data exchanges, analysis, qualification methodologies, so that we can move these from the high volume domains where you can clearly justify the cost of doing whatever it takes to get that latest processing capability into the data center and satisfy those needs, right? To the lower volume applications, where we just don't build as many compute nodes as we build F-35s. That's probably a good thing. But we have to figure out through standardization and standardization of both methods and interfaces and all of these things, how we can use these technologies in high volume, medium volume, and low volume applications. Because today we don't look at IC technology and say, well, that's only for the high volume applications. But here today, I think that's kind of where we stand. I kind of argue that we're in the early stages because I feel like we're kind of in the mid stages, right? Because, like I said, you know, the 2.5D devices were being flown in the F-35 almost 8 years ago, right? In the early trial phases. So that's not early. It's more towards the mid phase. So it's time to grow up and standardize our methodologies and our processes so we can do this in all volumes.
You know, as a founder person, I think packaging is an example of one of the biggest disruptions that we've seen, because packaging was very tightly held secrets. IDMs did their own packaging, and they didn't share. And some of the packaging was farmed off to third-party manufacturing facilities, and it was all very secret. TSMC started sharing packaging with their ecosystem, right? So they started working with customers and different partners, and everything became open. And now, if you look at Intel and Samsung, two of the biggest packaging houses, now they're opening it to everybody. So it is a huge collaboration. It's part of an ecosystem, and I think that's why packaging is probably one of the most interesting markets, or the technologies that we're going to see that are going to help us scale up. Well, I'm just very happy to be in this panel, but I really do think packaging is a very big deal. But I agree and disagree. I think it's just the beginning. I really do.
I can tap onto that a little bit. You know, for many years, I've been leading our advanced node boundary enablement for regular 2D, and so really up close on all the interactions with boundaries. Definitely see change in you mentioned the CapEx investment, the technical investment as well, in bringing that up. So it certainly, you know, and my reflection shifting over to 3D is also kind of a reflection of that, and looking at what's next. So I would agree with you. I also agree 2.5D is not new. You know, I think that one we feel is a little more scaled out, and you know, looking ahead at 3D and all of the kind of challenges ahead. I think there's going to still be a lot of innovation that we still haven't even thought about yet.
Yeah, if you notice, like AMD, the latest supercomputer, the Frontier, is based on MI200. That's the 2.5D. And then we all already announced the next generation of Frontier, that's MI300, and then MI300 is 3D. So back to the question earlier on, that are we ready? I think we're there. Yeah, from the design point of view, it's there, and AMD really, we ship in high volume, right? It's not like a few 100,000 or something, right? So 3DIC is real, it's here. The issue is the tools that used to do validation, I think, is behind the curves, and that is the issue, right? I think from the hardware design, from the packaging, they're all there, and it's already happening. And I think it's for EDA vendors and for us working in methodology and CAD and all that stuff, we need to catch up what's going on with the reality, right? So that's what it is.
I mean, so it was mentioned, but the high performance compute clusters that are running these analyses have to scale up so that we're not having to make difficult choices of doing EMIR analysis in a block-based methodology across the chip, because we can't do the whole chip, right? Take that and extend that.